Okay, sorry, question? Yes, you can. So we're going to start Unit 2 here, but we're not going to get too far into it today. Okay? We're just going to talk about some of the basic ideas for the dynamics unit. So in the dynamics unit, we're going to look at a lot of the same type of movements that we looked at in the kinematics unit, but in the kinematics unit, we only analyze them at kind of a basic level where this object went here and it went this fast, or it accelerated like this. Okay? In the dynamics unit, we look at why. Why did it go that direction? Okay? Why did it accelerate or travel at a constant velocity? In terms of the forces that might be acting on that object and the work that's being done to exert those forces. Okay? So where does the energy come from? Okay? Things like that. So we're kind of analyzing more the internal parts, okay, of the movements now, as opposed to just the stuff that's kind of obvious to see. Okay? So the first thing we got to look at is, oddly enough, Newton's first law. It's the first thing that we do, okay? Because it governs what happens to an object if there's no net force acting on it. Okay? So basically, Newton's first law says that this desk right here will stay right here, provided nobody bothers it. Okay? If I kick it, then it's going to move, but I bothered it. Okay? Up until the point where I kicked it, were there any forces acting on it? Gravity was acting on it. What else? It's tougher to come up with the second one. We can get gravity because gravity's always pulling us down. Stupid gravity's always working against us. Okay? But yeah, gravity is pulling on the table or on the desk. But if gravity is the only thing acting on an object, what should that object be doing? Falling. Desk's not falling. What's keeping the desk from falling? The floor. Okay? So there are actually two forces acting on that desk right now. The force of gravity pulling it into the floor, and the force of the floor pushing it back up. Okay? You ever heard that expression, every action has an equal and opposite reaction? That's Newton's third law. We'll get there in a couple of weeks. Okay, we're not there yet. We'll get there in a couple of weeks. Okay? So this desk right now has no net force acting on it, no unbalanced forces, because the force of gravity is being balanced by an equal and opposite force from the floor pushing upwards. Oddly enough, this is also how you jump. Okay? Which way do you push if you want to jump? We don't think we push up because that's the way we go. Which way do you push? Down. You push down. Yeah. If you want to jump, you push hard on the floor. Okay? Bend my knees and I exert this force and I press on the floor. I'm not going to jump. I used to be able to jump, but now I'm old. I have a credit card vertical and I'm embarrassed. Okay? So, yeah, you push down on the floor, okay? And the floor has to do what? Every action has an equal and opposite reaction. If I'm just standing here, the force of gravity and the force of the floor are balanced. But if I push on the floor harder, the floor has to push back harder, and that will overcome gravity and shoot me into the air. That's how I jump. Okay? You're never going to look at the world the same after you take physics. Okay? My wife always tells me that. She's like, well, that's really interesting. And then I switch into teacher mode and start explaining why. She's like, you look at the world so differently. And it's true. Okay? Once you start learning about physics, you start seeing the world a little bit differently. It's not going to be like horribly intrusive unless you're like me, okay? But it's different. Okay? You'll start seeing those forces a little bit more and understanding why things happen as opposed to, oh, that was really cool. Okay? That was really cool, and here's why it happened. Okay? All right, so the idea of inertia is this. An object at rest, like the desk, will remain at rest unless acted upon by an external unbalanced force, or a net force. An object in motion will remain in motion at a constant velocity unless acted upon by an external unbalanced force. Okay, this is important. The part about traveling at a constant velocity, because it has a lot of implications for safety. It's been pretty icy this winter. Okay, you ever notice that when it's really icy, you hit the brakes and it appears like nothing happens? That's Newton's first law, preparing to kick your butt. Okay, because you have inertia, you have a tendency to continue moving forwards at a constant velocity, because that force that normally stops you, friction, isn't there. Or it's not there like it usually is. Okay, there's a little bit of friction always.
Is that why it feels weird when you're like driving on the highway and it's like a weird sharp turn and you're going really fast and you kind of feel like you're going to go forward, but you're like, it's sometimes a weird feeling.
It is. It's also why that does sometimes happen. Why, like when you turn the wheels but the car keeps going straight? I'm sure you've all had that happen, right? You corner too fast when it's icy, okay? Wheels are cranked, brakes are on, car's still going straight, okay? What are you supposed to do in that situation?
Accept your fate.
Okay, partially, yes, partially accept your fate. What else?
Put in neutral.
Okay, you could, but that's not really gonna help at this point because there's no traction.
What did you say?
Okay, you could, well, certainly let off the brakes. Okay, even with anti-lock brakes, there's some situations where all you get is that really unsettling sensation of the brake pedal pushing against your foot and nothing happening. Okay, yeah, back off the brakes. And because our natural reaction is totally the opposite of what we should do. Okay, we want to turn and we don't turn. So what do? We crank the wheel harder and we depress the brake as hard as possible. Those are the two things we don't want to do in that situation. There's no friction, and all you're doing is making that worse. Okay? You want to ease off on the turn, because then you might get your wheels pointed in a direction where there is going to be some friction that would allow you to possibly change your direction. Okay? Because they would be rolling again. The reason you're not turning is because your wheels are sliding and not turning. Okay? The whole point of anti-lock brakes is to keep the wheels turning so that you can steer while slowing down. Okay, does everyone kind of follow me there? In perfect road conditions, actually locking up the brakes and like skidding to a stop is generally going to be quicker than rolling to a stop. The advantage of rolling is that you can steer around a possible obstacle, you know, like a small child or something, like, you know, that you don't want to hit, okay? Because there's things like that out there. Okay? So yeah, our natural reaction is that we do these things, and they're because of Newton's first law. Okay? Also why we have a seatbelt law. Newton's first law is what kills a person who is not belted in. Because if your car hits something and it stops, and you're not seat belted, Newton's first law applies. An object in motion will remain in motion until acted upon by an external unbalanced force. You know what those forces are? Steering wheel, windshield, hood, other car, road, all things that will change your shape in an undesirable way if they exert a force on you. Okay, that's why you are almost always, and by almost always I mean 99.9% of the time, better off in the car in an accident. Okay, it's also why in a rollover, okay, if you get ejected, what kills you? Your own car. Your own car will roll over you in a rollover if you get ejected. Okay? Because if your car is doing this and rolling and you're not seat belted in, you will be thrown in a straight line tangential to the direction of the car, which means you will do this. What's slowing down faster? You flying through the air or your car rolling along the rough ground? The car. So you'll get ahead of it. And then it'll roll over you. You're better off in the car. Okay? Better off in the car. Always safer to be seat belted than not. Okay? That sort of makes sense? All of the devices in your car that are designed to save your life operate on Newton's first law. Okay? How many people have ever gotten in the car and they pull on the seatbelt? You're in a hurry, right? Pull on the seatbelt and the seatbelt won't come out. Okay? And then what do? And you just keep pulling, or you keep pulling harder, and you have to back off. Let it go back in a little bit and pull it away. Okay? So what happens with a seatbelt is you actually have a pendulum. Okay? And the pendulum is on a hinge. And then there's like a wheel and a locking bar. So there's a locking bar here, and then there's a wheel that's ratcheted. What am I drawing that for? I have a picture. I can't draw, I should know my limitations. There it is, the picture. Okay, so this is the mechanism that your seatbelt locks with. If you're traveling at a constant velocity, the pendulum is straight up and down. As soon as you hit the brakes, the pendulum swings forward because it obeys Newton's first law. It's in motion. It tries to stay in motion. So it swings forward, tilts up the locking bar, which catches that ratcheted wheel that was the bane of your existence when you were in a hurry, okay, and doesn't allow the seatbelt to unroll. Okay? When you're in a hurry and you just pull on the seatbelt really quickly, all you're doing is you just jar the whole mechanism really violently and it just locks. Okay?
Why is it when you pull the seatbelt really far and then pull it back in to lock?
Sometimes it's just a matter of, again, jarring the whole mechanism. You just get it too far. Because there's a little bit of play in the lock, in the ratcheted wheel. So when you've got it all pulled all the way out, and you can pull the wheel up enough that it'll catch on the locking bar. Okay. This is also how airbags deploy. Okay. There used to be, when airbags were first designed, it was a contact switch. Okay. So if you impacted something, it would, the front of your car would squish in, and then it would complete the circuit and detonate the airbag. Okay. Now that airbag works on the same mechanism, not a pendulum, but more like the mechanism that tells your phone which way you're holding it. Okay, it's the same kind of a sensor, because they found that the contact sensors could be set off in situations that they were not required for. Okay, like I couldn't find the video the other day when I was looking for it. There's this video of an old lady with a walker, and she's going across the street. She's really, really slow, and there's this guy in like a convertible Mercedes, and he's like honking at her. It's just like really, really rude and mean. She's going as fast as she can, and just keeps honking and honking. She takes her purse and swings it into the front of the car. Boom! Airbag goes off in the guy's face. Right? It's like, oh, karma. Okay? But yeah, like when they were a contact switch, that could happen. Okay? Even just bumping into the front of the car could accidentally set off the airbag, which is of course not desirable. So now they're on an accelerometer. Okay? And so if you stop suddenly just by slamming on the brakes, the thing will move forward, but it won't touch the switch and it won't activate. But if you get in a crash, the acceleration is sufficient that the circuit gets completed and boom. Anybody been in the car when one of those goes off? It hurts. Yeah, but it hurts less than the steering wheel. Okay, and it's loud. It's really, really loud. And you'll get marks. If you're the driver, you get marks on your arms because the explosion is so violent that it hits your arms really hard and will leave bruises on your
Can you
arms.
like knock yourself out if you're driving with one hand or two hands at the top of the steering wheel? 'Cause then you'll just
Probably. Yeah.
Don't like a lot of people like break their noses if they're not sitting right? Like,
Could be.
Oh, my goodness.
Yeah, I mean, there's a certain distance that you're supposed to sit from the steering wheel that's safe. It's like basically your arm should only be bent slightly. Like, because you see people and they drive like this and they're right up against the steering wheel. That terrifies me. Okay, have a good weekend, guys. Hey, try not to be out and about when the snow happens. It's gonna get real bad. Think Newton's first law and how it will affect your driving.